Customer and market focused is next. I've said it again, I'm saying it now. It is necessary to understand who the customers are and what their needs and wants are. Your wants, your needs mean nothing. It's your customer wants and needs. So how are you going to understand what the customer wants and needs are? Well, you've got your warranty claims where things are coming back with problems and product returns. Those are giving you feedback. But you should also have helplines, customer service centers, have times where you actually talk to customers to find out how their needs or wants might be changing to help you make the changes and quality changes to make a better product. Work with your suppliers. We'll talk a little bit later in the semester about JIT2, just-in-time 2, which is actually working with a just-in-time attitude with your suppliers and making sure that you have what you need. If you're not getting quality raw materials from your suppliers, you have a problem. If you're not getting what you want, this is what you're working with and why you need to work with your suppliers and focus on the market. What are they at? What are the trends? What are the changes? What do people want? Growing up, I had, we started with the radio and records, and then we went to cassette tapes. Now there's CDs out there, and now you can just download. Do you even buy CDs anymore? Compare your product with your competitors. How are you quality-wise, cost-wise, with your competitor? Who has the most market share? All of this is what you want to take a look with when we take a look at the market focus. Next is process management. And this actually takes a look at a systems theory. Now, systems theory takes a look that the whole system is interconnected. When you have a problem in one area, other areas will either be affected or compensate for that. So the company works together. It's a web of interrelated processes and sub-processes. And that's literally what the systems series looks at, how one affects the other. Your macro processes, your strategic management process, your improvement, your input, your order achievement, your order fulfillment. How do you do these? How are you managing these processes? Product development, starting with analysis. Developing your problem statement, identifying stakeholders, identifying needs, conducting your research, determining your scope and schedule, taking a look at your requirements, developing your requirement documents, developing your functional documents, development use cases, development system architecture, identify alternatives, and then taking a look at design. Develop alternatives, comparative analysis, develop preferred alternatives, moving on to implementation. What's your business plan? Doing testing and integration, conducting testing on that, and delivery last, develop technical development for the presentation and a project website. And you can move up and down this project development multiple times to make sure that things are right, to make sure that things are working as they need to do. You can take a look at quality function deployment, which is a methodology for development or the evolution of the features, attributes, and characteristics of a high quality product. Again, we're focusing on our customers' needs and desires, your customers' wants, your customers' needs, not yours. To make sure you're hitting those product levels, that quality level for your product. What's the technology that's involved with this? Computer-aided design, computer-aided engineering, computer-aided manufacturing. Believe it or not, approximately 70% of a product cost is in the design of the product. Before we even get to engineering and manufacturing that product, it's the design of it. We want standardization, fewer choices of components and products to produce. The fewer we can produce, the better, and we want simplification, having no parts than are necessary. And how do you memorize standardization and simplification? You use giving gifts. If any of you have children or you have friends with children, do you know how to give a gift to them? We take a look at someone you like. You give their child something that doesn't make a lot of noise, has very few parts in it, and doesn't need batteries. If it's somebody you don't like, if there's 102 pieces, it uses batteries constantly and drains them all the time, or it makes lots of noise. The better product is standardized and simplified. Just like that better gift to give to someone that you like, has few moving parts, doesn't break, they can't lose them, and it doesn't make a lot of noise. It's simple. So you take a look at that to reach standardization and simplification. Reliability is one aspect that must be considered when we take a look at design. And my father was actually a reliability engineer. He worked up, if anyone's flown through Pittsburgh Airport, they have the people movers from Concourse E to ABCD, and it's what they call the people mover. It's actually sort of like a little subway car that goes underneath the tarmac over to what I call the puddle jumpers, the small planes, commuter flights versus the larger planes. But what they're looking at is mean time between failures. We actually engineer failure when, preferably after, the warranty is up. But we're taking a look at the average time lapse between repairs. When do you need to do repairs? What my father looked at was, when do the tires need to be changed so you don't have the blowout or a flat tire on these people movers, because you're in a tunnel underneath where the planes are, going from one concourse to the other. So you want to take a look at how you can engineer in failure and how long you have to know for repairs. If you have a car, how often do you change your oil? Every 3,000, 4,000, 5,000 miles, depending on the car and the oil that you're using. This is a repair. When you're looking at machinery, you want to do regular maintenance so you don't have these failures, or so that something doesn't break in the middle. You need to search for a consistent on-target performance. How? We're going to set tolerance limits. And we're going to talk about those in just a little minute, but our upper specification limit and our lower specification limit. And a lot of times these are also called control limits. So hold on to that thought. We'll come back to it in just a minute, because we need to figure out, why do we need our specification or control limits? And that's because there's variance. Things vary. Sometimes it's chance cause, random and uncontrollable. When you put on an oven and you heat it up to 350 to bake a cake, is that whole oven at 350, or is parts of it at 375 and parts of it at 325, depending on, did you just open up the door, the back of the oven versus the front of the oven. The front of the oven might be a little bit cooler because there's some leakage out that door, things like that. There's assignable causes caused by controllable means. We know we can fix some of these, some of them we can't. And inherent causes, chance caused and must be within our upper and lower specification limit. Any item that is not within those limits is not acceptable. Okay? If it is not within our upper and lower specification or control limits, it is not acceptable. So let's take a look at that. We have a chart here, and when we take a look at this chart, actually what we are looking at is the normal curve turned on its side. We have our standard deviations going up and down, and our mean in the middle. This is based on a timeline. Each one of these is a set time. And I'm going to say either a timetable or a time bucket. We'll be talking about time buckets later in the semester. But it's what it's looking at. And it has to stay within our upper control limit or specification limit and our lower control or specification limit. It needs to stay within these lines. If it does not stay within these lines, it is not in control. It does not meet our specifications, and it's not a good quality product. When we take a look at this, we have certain things that tell us things are out of control or moving out of control. If something falls outside those two lines, it is out of control. Stop your procedure right then and there. Fix what's happening. Find out why this process is not in control. Things that show us that something's happening, that we're moving out of control, and we should stop and find out what's going on right away, is if sample values are not distributed across the chart, but are all on one side of that mean. And depending on your author, it's usually between 4 and 6 occurrences, all on the same side of the mean. It's considered moving out of control, and you need to get it back in control as quickly as possible. Another thing is when there's more than 4 standard deviations between one sample and the next, between that time limit. This is moving out of control. Something has happened that we're having a problem here. We're still within our specification limits, that we can still use that product. It's still a good product within our quality, but there's a good possibility that the next one won't be, and we want to make sure that we get whatever it is fixed. Lastly, moving out of control, when you have 4 to 6 observations in a row that are moving in a line, whether they are going up or going down, it doesn't matter. But when you have 4 to 6 of these moving in a line, we know that it's moving out of control, and it will quickly be outside of our control or our specification limits. So we want to quickly find out what's going on to fix this so we don't produce poor quality. Remember before we talked about prevention, appraisal? This is the appraisal side. We want to get things worked well before they move into an internal failure, because that's going to cost us more money. Again, if on these 3 we are moving out of control, it is not out of control yet, we're still producing quality product. Here, we are not producing quality product because it's outside of our control limits. That needs to be stopped immediately to find out what's going on. And we need to scrap, that's an internal failure. We need to scrap that item so that it does not continue to be made poor quality. Little review here, because you're going to be using standard deviation, and I have found out that some of my students have a problem with standard deviation. So when we look at standard deviation, we take the square root of the sum of each and every single x minus our mean x bar, then we square it, divide it by n minus 1. We are using a sample here, not a population, and then take the square root. I put this out into steps for you. Start by finding the mean. That's x bar. Subtract the mean from each observation. Take x, each and every x, and minus x bar. Next, take each x minus x bar and square those. Take all the answers you got in step 3 and add them together. That's summing it all up. Subtract 1 from the number of observations. Remember, n is our number of observations. Subtract 1. Divide step 4 by 5. So we are taking our sum x of x minus x bar squared and dividing it by x minus 1. Lastly, we're going to take the square root of that number we got in 6, which is the sum of x minus x bar squared divided by n minus 1. All of this is underneath that, and you're going to get your standard deviation. Again, this is using a sample. This is not using a population. We will be using sample sizes in here. Why do you need to know standard deviation? because you're going to be working with a process capability index. The process capability index tells us something is capable, a process is capable of working or not. It uses upper specification limits, lower specification limits, and standard deviations. Now again, we said that we're using three standard deviations on either side. This right here is our upper specification limit, our lower specification limit, and our X bar. All I've done is turn this on its side to give us the three standard deviations on each side. So there's three standard deviations going up and three standard deviations going down to the lower specification limit, which give us a total of 6 standard deviations within our specification limits. So let's take a look at this problem. The specifications from the manufacturer of a particular type of metal coating call for the temperature of the drying oven to be 370 plus or minus 10 degrees Fahrenheit. So 370 degrees plus or minus 10 degrees Fahrenheit. The company that is considering using this coating has run tests by taking a large number of temperature readings from various parts of its oven at random times. The standard deviation of the readings about the mean temperature setting was found to be 2.06 degrees Fahrenheit. What is a capability index, and is this process capable? Well, this is really nice. It's giving us the standard deviation of 2.6. We have to figure out, using this right here, our specification limits. So doing that, the problem again is just written right here on the side. We're going to take a look at our capability index, which is our upper specification limit minus our lower specification limit, divided by 6 standard deviations. Starting, we need to find our specification limits. Our upper specification limit is going to be 370 plus 10 degrees Fahrenheit, which last time I knew was 380. Our lower specification limit is going to be the 370 degrees minus 10 degrees Fahrenheit. That should be it. Which is 360. We're already given our standard deviation, which is 2.06 degrees. Okay? I like to do plug and play. I have all my information over here. I can now plug it into my formula and run the numbers. I find it a lot easier than trying to figure out what it is I need to put in as I go through the problem. I want to figure out as much of it I can before I plug in to my formula. So my capability index is going to be my upper specification limit, which was 380, minus my lower specification limit, which was 360, divided by 6 for 6 standard deviations, my standard deviation, which is 2.06. If I do the math on here, my capability index is 20 divided by 12.36. 20 divided by 12.36 is approximately 1.618. Is this capable? Well, I haven't talked about that yet. Let's talk about it. A capability index, which is greater than 1.0, is considered capable. A capability index less than 1.0 is not capable. Capable. Where does that leave 1.0? Some say here, some say down below. For this class, if it hits 1.0, we're going to call it capable. Now, how many of you have ever heard of lean manufacturing? Lean manufacturing, or Six Sigma, uses a capability index at or greater than 2.0 to be considered capable. I would like you to know this. We will not be using it in this class. We will just be using a capability index of 1.0 to consider it capable, the process capable, but I would like you to know that in Six Sigma, they do use a 2.0 capability index. Now, if our capability index is 1.618, it is greater than 1.0, so this drying oven and the coating, the process will work. It is capable of working. You still have to make sure that you stay within your control limits and make sure everything works out. Business results. We're going to take a look here at our change in market share. What happens with, and this is still part of the Malcolm Baldrige Award, what happens if our market share goes up? It means we've got more market share. If it goes down, we have less. What's happening to our market share? What's the complaints and warranties claims that we have? Are we following up on them? Are we doing a good job of following up on them? What type of surveys are we taking? What type of information are we gaining from our customers and those who are our potential customers to know what we want, what we need to do to make sure that we have their wants and needs forefront in our mind and making sure that we're producing a product that meets those wants and needs? And what's the ability to balance those interests with other stakeholders? Who are our other stakeholders? Our other stakeholders are our shareholders. They're our employees. They're our suppliers. They are businesses that surround. ETSU has other stakeholders than just students. They have the staff, they have faculty, they have the businesses that are around us. The Carnegie gets a lot of business from the university, so they're actually one of our stakeholders. PALS, that's across the street, a lot of their business comes from ETSU. So we're one of their stakeholders. So you need to take a look at how it's going to affect all of these people, suppliers included. Six Sigma, we talked briefly about lean manufacturing, or Six Sigma. The quality management program emphasizing the application of analytical tools and widespread involvement of employees across the organization. We want to take a look at how we can improve, control, analyze, define, measure, all of these things to make sure that we create a quality product. We also want to use what's called DMAIC, which is define, measure, analyze, improve, and control, which is the emphasis of Six Sigma. You want to define your problem and objectives. Measure, what do we need to improve? Where are our improvements needed most? Analyze the process and factors of influence. You need to know what your process is before you can improve upon it. Then you can move towards implementing your improvement, and then assure that the improvement will sustain. Control, make sure that the improvement was actually an improvement. We can investigate quality, different things using cause and effect chart or a Pareto chart, taking a look at these things and how this is also, this one is also called a fishbone chart, taking a look at how these things work together. The Pareto chart, what are the reasonings behind it? What's causing certain things? We can take a look at correlation coefficients. a measure of the strength of any linear relationship between two sets of operations. We have the formula here, and while you will not be working on problems, you do need to know how to interpret an R score. So if we have an R is going to be in between 1 and -1. Actually, it can be equal to either one of those. If we have no relationship at all, we're going to have a graph like this and no correlation, and our R will equal 0. If we take a look where one thing rises and the other rises, that's going to approach a 1. A negative correlation is where one rises and the other goes down. When we take a look at correlations, if our R is between a 0.2 and a -0.2, we're going to take a look at a weak relationship, very weak relationship to no relationship. If it is around a -0.5 or a +0.5, then it has a relationship. At a -0.8 and a 0.8, it's considered an extremely strong. We've got a very strong relationship there. So closer it is to 0 is no relationship. Closer it is to -1 or a 1 is the either strong positive, strong negative relationship. Taking a look there. So you do need to be able to interpret these R scores. Looking at the sustainability and product development, we start off with cradle to gate. Sustainability is how long can this product last? How is it good for our environment? We're looking at a variety of things. Cradle to gate is planning sustainability from the procurement of raw materials through the production of the product. We want to make sure that our waste for this product is not necessarily bad for the environment, using things that it shouldn't be using, looking at that. Cradle to grave is planning sustainability from the procurement of raw materials through the final disposal of the product. And cradle to cradle is planning sustainability of a perpetual cycle of transformation in which the disposal of one product provides the materials for another. So when the product is no longer any good, it becomes something that's good for, or the raw material for another product. So waste becomes a raw material for another product. The scrapping and throwing away, it now can be recycled, become another product, etc. That's taking a look at this chapter. We'll move next time on to forecasting, and I hope you have a great day. Thank you.